Okay, so we've worked through all of the examples of graphing polynomial and rational inequalities, but now to answer the million-dollar question is how is this actually applied in a real-life setting? Now, my examples here aren't most likely going to be something that you will see in your day-to-day life, but you can see examples of where this does show up in a real-life setting. So I have example 1. We are trying to make a rectangular quilt. So this works with anything rectangular. So if you're not into quilting, maybe you're going to think about making a rectangular garden or something along that sort. Is to be made that the length is 1.2 times the width. The quilt must be between 72 feet squared and 96 feet squared to cover the bed. Determine the restrictions on the width, so we're looking for the dimensions or the restrictions on the width, so that the dimensions of the quilt meet in the required area. Give exact values and approximated values to the nearest tenth of a foot. So I think this is a perfect time to pause the video and see if you can determine the restrictions on the width on your own. Okay. So the key parts to this problem, as I said before, it's rectangular. We want to talk about the area here since we're talking about feet squared. So we know that we're going to be talking about area of a rectangular region. Well, that is just going to be length times width. We also know that the length is 1.2 times the width. So the length is, anytime you see an is, that's an equal sign, 1.2 times the width. So I can just take this length equation and plug it in for L right here. So that gives me my area as a function of W is 1.2 W times W, or 1.2 W squared. Now I need to determine how big my width of this quilt could be. Well, I know that the area has to be greater than 72 and less than 96. And so I'm just going to set those up as two individual inequalities. My first one, my 1.2, my area has got to be greater than 72. On the second one, my area has got to be smaller than 96. Okay, so now I have polynomial inequalities, and it's going to be that easy to simplify. So on the left, I can, or on both of these actually, I can just divide by 1.2. And so my first one gives me W squared is greater than 72 divided by 1.2, which is 60. And then over here, W squared is less than 96 divided by 1.2 is 80. Okay, now I can square root both sides. Technically, when I do that, I need to insert my plus or minus, but I'm talking about width here, so width can only be a positive, so I'm only going to look at the positive version of these. If I look at square root of 60, I can simplify that as square root of 4 times square root of 15. So I know my W, or my width, has got to be greater than 2 square root of 15. On the left, I can take square root of 80 and simplify that as square root of 16 times square root of 5. And so that tells me W is less than 4 square root of 5. So once it wants the exact values, these are my two answers. The width of my quilt must be greater than 2 root 15, and it also must be less than 4 root 5. So that's my exact values. Now, it also wants the approximated values, right? Because if you told these numbers to somebody, they probably would have no idea what they are. So let's figure out what they are approximately. So I know that my width approximately has to be greater than 2 times the square root of 15. Just typing that in my calculator. And that gives me 7.74. It says to the nearest tenth of a foot. So that is 7.7 feet. And then my other here, 4 times square root of 5 is 8.9 feet. So I have my exact values in yellow, and I have my approximate values here in green. And so you can see how easy this is in real life. What exactly are we looking for? I have one more applied example for you, but before I actually give you the example, I need to do a little setup before that. And that setup is just saying if we're talking about vertical position of an object traveling upward or downward that is influenced by gravity. So basically that's going to make the parabola motion. So if you throw a ball up in the air, it's going to have this motion here. So if you throw a ball up into the air, it's going to come up and then it's going to come back down. So the parabola shape. Or if it's going to have the opposite shape, then of course it would be the parabola going the other way. Okay, so we know parabola, so of course this is going to be a squared. Well, what's the rest of these values mean? S is just the position. How high is that whatever we're referencing? If we're talking about the ball, how high is the ball up in the air? T stands for time, so this might be the ball after 0 seconds. This is the height of the ball after 1 second. This might be the height of the ball after 3 seconds, so on and so forth. So T stands for time. And then the rest of these. So G stands for gravity. That's why this is under the influence of gravity. If we're working in feet per second, the number that we're going to substitute in for there is 32. If we're working in meters per second, the number that we would substitute there is 9.8. So it's either one of those two numbers, and that will never change. This V sub 0 is the velocity, which is either positive if you're throwing it upward like this, or negative if it's moving downward like that. So velocity is the rate. How fast is it moving? And then the last thing that we have to plug in is the initial position. So this person that's throwing the ball, are they standing on the ground? Are they standing on a building? Or how high are they when they actually start to throw this ball? So here's the formula that we're going to use for our example. A toy rocket is shot straight upward from a launch pad 1 feet above ground level with initial velocity of 64 feet per second. So we need to write a model, meaning we need to write a function or an equation of the vertical position given by that formula that I just gave you of the rocket t seconds after launch. So t stands for time. Our time is in seconds in this. We also know that we have an initial height of 1 feet above ground level and a velocity of 64 feet per second. So our generic equation was S of t equals negative 1/2 gt squared plus our velocity times t plus the initial time. Okay. Well, let's plug in what we know. If it starts at 1 foot above ground level, that's our initial height. If it's a velocity of 64 feet per second, then that's what we're going to plug in for the velocity. And then for our gravity, remember we had two choices. If we're in feet per second, then we're going to use 32. If we're in meters per second squared, we would use 9.8. This problem is in feet. It shows us a couple of times. So we're going to use 32 feet per second squared here. Okay, so our function is negative 1/2 times 32 times t squared plus 64 times t plus 1. And so the only thing I need to do to simplify this is multiply by my negative 1/2 times 32. And so the function that we're going to use is negative 16t squared plus 64t plus 1. So we have our function set up. Now we need to determine at the times in which the rocket is above a height of 50 feet. So if I give you an image here, here's our rocket. Okay, here's our ground level. This is 1 foot above ground level, so this is 1 foot here. Our rocket shoots up, and then it comes back down. So we want to know at what times in which the rocket is above a height of 50 feet. So it starts at 1 foot. So we want to know if we move up here to 50 feet, At what times is it above my 50 feet? So we're looking for this part of the graph. So we need to figure out what this time is, and we need to figure out what this time is. And so this x-axis is actually a representation of time. So to do this, we just take our equation, negative 16t squared plus 64t plus 1, and we set it above or greater than a height of 50, greater than 50. So there we go. We've set up our polynomial inequality. Now all we need to do is solve it. Move my 50 over here to the left, so it gives me negative 16t squared plus 64t minus 49 is greater than 0. We could try and factor it. Unfortunately, this one does not factor, so that means we have to solve it by completing the square, or my preference is the quadratic formula. T is equal to my negative b plus or minus square root of b squared, which is 4,096, minus 4 times my a value times my c value, all over 2 times my a value. So it gives me negative 64 plus or minus 64 squared, which gave me this 4,096, minus 4 times 16 times 49, which is 3,136, all over a negative 32. So 4,096 minus 3,136 is negative 64 plus or minus square root of 960, all over negative 32. Gives me negative 64 plus or minus 960 divides by 64, so I'm going to divide it by that. That leaves me with the square root of 15, all over negative 32. Gives me negative 64 plus or minus 8 root 15, all over negative 32. And to simplify this, let me simplify everything by, let's see, 8 goes into it. So negative 64 gives me negative 8. This 8 divided by itself cancels to give me 1. And negative 32 divided by 8 gives me negative 4. I can also simplify some of my negatives here. So I can cancel these out, and really that cancels these, but it just flip-flops them. So that gives me 8 plus or minus root 15 over 4. So that's going to be my dividing values here. My left-hand value is going to be 8 minus root 15 over 4, and my right-hand value here is going to be 8 plus root 15 over 4. And so this is where it goes above my 50 feet, and this is where it starts to go below my 50 feet. But we need to make sure that our signs actually do match up, that with this one is negative, positive, negative. So we need to put our sign chart in here, and it might be easier to figure out what these are approximately. 8 minus root 15 divided by 4 is approximately when time is 1.03, and 8 plus root 15 over 4 when time is approximately 2.96. So I'm going to put my exact values here because exact is always more precise, but I can know my approximate values. So less than this here is less than 1.03, so I'm going to do 0. In between is in between 1 and 2.96, so that will give me 2. And beyond this, beyond 2.96, anything beyond that, I'm going to do 4. What am I going to plug it into? I'm going to plug it into this equation here. Unfortunately, there isn't a ninth factored format of that equation, so we're just going to have to plug it in the equation itself. So I will let you do that work on your own. 0 is really easy to plug this in. If I plug 0 in, of course, I just get out negative 49, so that's going to give me a negative here. If I plug 2 in, it gives me negative 16 times 2 squared plus 64 times 2 minus 49. If you do all the work, that you see that that's positive. And last, if I plug 4 in, negative 16 times 4 squared plus 64 times 4 minus 49. If you do all the work there, you see that that comes out to be negative. So, of course, our middle interval is positive, and so when all of these values are between these two values is when it's above our 50 feet. So our answer then is when the time is between those two values, 8 minus root 15 over 4 and 8 plus root 15 over 4. And if you wanted approximate values, then that would make perfect sense. Between approximately 1.03 seconds and 2.96 seconds. Sorry, that's kind of all mumbled jumbled in there. I ran out of room. So there is my final answer. And of course, you're always more than welcome to graph this to see if your answer matches what the graph claims it to be. And now we have finished up solving polynomial and rational inequalities, including where might this actually happen or where might you use this in a real life setting.